In this video, we are going to continue our discussion of Chapter 5, Section 1, Exponents and Logarithms. In particular, we saw in the first video the first two objectives, just understanding what exponential notation is, and then the relationship or the correspondence between exponential functions and power functions. We saw that all the facts were the same. They're just based on the exponent rules. However, we just put the variables in different locations of those facts to emphasize what we're interested in. Are we interested in the base, or are we interested in the exponent? In this video, we are going to address the third of our 5 objectives, looking at the correspondence between exponential functions and logarithmic functions. Now, short piece of background history. You go to the 1600s and people were working with exponents. And what they figured out were, hey, adding and subtracting is really, really easy. Multiplying and dividing isn't. Well, in the 1600s, there was a mathematician named John Napier who came up with a different notation for writing down exponential functions. Basically, it's still designed to emphasize the exponents, but instead of writing the exponents with a tiny little number and the base number being so large, for instance, instead of having it written like this, where it seems like the variable of x is less important than the base of 10, because the base is written larger, John Napier decided, I want to write this same fact using a different notation, and by writing it in a slightly different way, we can emphasize things more differently. That's what we're going to look at today. What is that connection that John Napier came up with? Well, let's start by looking at a couple of facts. 10 to the first power is equal to 10. 10 squared is equal to 100. 10 cubed is equal to 1,000. 10 to the negative 1. We know negative exponent means 1 over, so 1 over 10. 10 to the 1/2 power. Remember, the 1/2 power means square root. So the square root of 10 is approximately 3.162. 10 to the 0 is 1. And more generally, we want to generalize these specific pieces to determine how John Napier chose to write out this fact. 10 to the x equals c. Ultimately, what Napier noted, we want to emphasize the exponent. We're going to consider problems where the exponent is the most important feature, and yet with exponential form, the exponent is written with the smallest number. Well, if it's the most important thing, then why are we writing it down as the smallest? That was basically the thought process. And so he looked at this and instead said, we're going to call this log of 10 equals 1. For the second one, he wrote it down as log of 100 equals 2. Log of 1,000 equals 3. With these 3 things, can we start to generalize a pattern? What would 10 to the negative 1 equals 1/10 look like? Log, and Brian, you chose to use a decimal instead of the fraction. Okay. 1/10 is 0.1. I personally would have written it as 1/10 with the fraction just because I like fractions more than decimals, but it's still absolutely correct. Log of 0.1 equals negative 1. Continuing further, log of, follow the pattern, 3.162 equals half. Moving down to the next one, log of 1 equals 0. Now noting, of course, with the logarithmic form, it's saying the same information. It's just writing the same information in a slightly different way so that we can emphasize something differently. In the exponential format, it doesn't look like the exponent is the most important thing. When we write it in exponential form, it generally looks like this number is the most important part because it's isolated by itself. It looks like, with exponential format, we're having a starting point to get an answer. Well, what if the answer we're looking for is actually the exponent? What if the exponent is the answer? Then this isn't a very helpful format then. Logarithmic form was created to emphasize the exponent as the end result. It was created to emphasize the exponent is the answer. All the rules we will do are still the exact same. We're just going to write them emphasizing exponents instead of emphasizing bases. Well, to finally finish this piece off, let's look at the very last one then, 10 to the x equals c. Generalizing our work, what's the rule that we're going to follow? Log of c equals x. Thus, one of the things we will note, we can convert back and forth between exponential form and logarithmic form depending on which one we feel is easier to do. And that's where we'll begin our next example. Solve this function. Noting, of course, this is a piece that we can rewrite in logarithmic form. How would this look then? Log of 10,000 equals x. Just rewriting it so that instead of emphasizing exponential form, we're using logarithmic form. And fortunately, we have our calculators for this. So let's pull out the calculator and check. And so we know we have to type in log of 10,000. Please notice right over here, this is the logarithm button. So we'll press log for logarithm of 10,000. Close the parentheses, and there's our x value. We got 4. Of course, did we really need the calculator to do this particular problem? Not really. By inspection, we probably could have figured out 10 to what exponent gives us 10,000? Well, 1, 2, 3, 4 zeros would have told us 4. Not a big deal. But if it were 20,000 instead of 10,000, it would perhaps be a little bit more difficult to see. And in that instance, if it were a 20,000, we could have taken our log of 20,000, and there is our answer now. So it, for the most part, just depends on which numbers we have, whether we're going to use inspection or a calculator. It's worth noting, this is not the only way to do this problem. there is an alternative property. Back here, we made the observation that exponential form tends to emphasize the starting value and then the answer. However, logarithmic form tends to emphasize the other direction, where the exponent is the answer and we're starting here. Well, I'm hoping that you notice that's a property that you've worked with a lot in your former classes. If you start with x to create y as the answer, and instead you go backwards, y creating x, that's a relationship that we've done a lot in algebra. In particular, things that undo each other are the inverses. You have seen in earlier classes, multiplying and dividing undo each other. They cancel out. They're inverses. Adding and subtracting cancel each other out. They're inverses. Squares and square roots cancel each other out. And now we have exponents and logarithms cancel each other out. Well, to try to take advantage of that, another way we could look at the same piece, because ultimately we need to recognize log of 10,000 equals x. Here's a different way that we could write this down algebraically. We could take a logarithm of both sides. The logarithm of 10, well, log and exponent cancel each other out. In the next video, we'll actually look at that in more depth and see why. But that gives us x equals log of 10,000, which should look very, very familiar. Same thing as what we just did. And so we'll wind up, of course, with the same answer, x is equal to 4. Let's consider this one. Log of x equals 6. Let's rewrite this then. Thinking back towards the notation that we had, log of x equals 6. What does it need to look like? Well, think of the positions. We're not so concerned about x and c. Those are just dummy variables. We're concerned with, in position c, we'll use the variable x. So in position c, we need to use x. Likewise, in position x, we have the number 6. So in position x, we need to have 6. Following the pattern that we just established, we know that this logarithmic format may be rewritten into exponential format. 10 to the 6th is equal to x. Now what is 10 to the 6th? 1, 2, 3, 4, 5, 6. And we have 1 million as our answer. We can convert back and forth between exponential and logarithmic forms. That is also not the only way to do it. We just noted previously logs and base 10 exponent. The exponent and the log will cancel each other out. As inverse, that's what they'll do. So how do we get rid of a log? Well, we need an exponent. So 10 to the log exponent. Exponents and logs are inverses. They cancel each other out. And we're left with x equals 10 to the 6th. Of course, that looks familiar. Once again, we would get x is equal to 1 million. Two different ways of solving it. Both of them are absolutely correct. And here's the last piece we have for this video. Get your graphing calculator, and we'll do these two things, not all four equations at the same time, but let's look at part A right now. y1 equals 10 to the x, y2 equals log x. So 10 to the x and log of x. And I'm going to graph both of these in the standard window. Looking at the graphs of 10 to the x, and now the graph of log of x, what do you notice? Let's consider a different window. Because remember, we saw problems with before with how far to the left that we had. Or rather, let me take this one. Y equals x. And let's graph all three now. What could you do to transform the blue 10 to the x into the red log of x? And instead of using the standard window, I'm going to use zoom square. Remember, we've discussed way back in chapter 1 that the graphing calculator has a problem because the number of pixels wide does not match the number of pixels tall. And so graphs get distorted because of that. However, if we choose zoom square, it will alter it so that it actually does look like a more appropriate graph. What behavior will take the blue to match the red? You notice it's a reflection. We can flip the blue across the line y equals x and match up the red. That is, 10 to the x is the inverse of log x, which we just noted before. This is just a graphical representation that they are actually inverses of each other. One of the reasons I wanted to point this particular piece out, there is an artifact going on with your graphing calculator right now. In particular, you notice with the blue with 10 to the x that we have a horizontal asymptote. Well, if you take a horizontal line and reflect it across the line y equals x, it will become a vertical line. There is a behavior on log of x where there is actually a vertical asymptote right here where it's going to start getting closer and closer and closer to the y-axis. However, because the calculator does not have the ability to handle numbers that are that tiny, the numbers have gotten so small, the calculator can't handle them. And so we wind up with an artifact that this vertical asymptote and all the behavior that I filled in is missing with our calculators. It's another instance where the calculator lies to you because it just can't handle numbers that small. By this point right here, it's already so close. By this point here, it's so close that the calculator legitimately can't tell the difference between that and an x value of 0. The numbers are too tiny. Let's now consider the same behavior. Instead of 10 to the x and log of x, there are two different buttons on our calculator we will use now. We'll use e to the x and ln. Please don't ever say the ln of x. As is frequently common, this is an abbreviation for writing. It is not an abbreviation for speaking. ln stands for the natural log. Please don't say the ln. Please don't say the ln of x either. It's just goofy and weird. And all right, so we're going to switch this one. Please notice where those buttons are located. Right beneath the log, we have the button here. Located in the blue, you should be able to see the e to the power button. So there's e to the x. And then we'll also use natural log of x. And we can then look at our graph and see a similar type of behavior. E to the x, the natural log of x, and the line y equals x, showing us the reflection, showing us that they are inverses of one another. An item worth noting, just like before, we have an artifact on the graph with an x with the logarithm, the natural log of x. At this point, we've gotten x values that are so small, the calculator can't determine their y values anymore. And so we will have a behavior where there is a horizontal asymptote, a vertical asymptote continuing down the y-axis. In your sketches, make sure you include that behavior. It is going on, the calculators just can't handle it. One last comment before we stop the video. What in the world is this thing? We changed it from the base of 10, a number that we know really, really well, to this random number, this random letter E. In this video, I made the assumption that you have a passing familiarity in previous classes, that you've seen the number E before. Many people are familiar with the number pi, 3.141592, blah, 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 where it keeps going. E is another number. It's approximately 2.718, blah, 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 and it does keep going like pi keeps going. E is a number that is massively important in mathematics. In particular, this is a pre-calculus class. When you get to calculus and you start doing a lot of your integration techniques, you start doing a lot of derivative techniques, basically whenever you start doing anything in calculus with exponents or with logarithms, the formulas are the easiest to use when you use this base E. The number E has many, many special properties that make calculus easier. So you will use it considerably, and with future lessons, we can actually go through later on at the end of the year. We will see where does this number E come from. I'm making the assumption that you've seen it before, you've worked with it before. We will address it again later on in the year, though. Thus, we'll conclude this particular video, noting that we addressed only one of the 5 objectives for this lesson. What is the correspondence between exponential and logarithmic functions? There are 2 of them. They are 2 different ways to write out our exponent facts. Exponential tends to emphasize using the exponent to get the answer, Logarithmic tends to emphasize the exponent is the answer. Since they work in opposite directions, those are inverses of each other. And just like you were able to use adding and subtracting to cancel, multiplying, dividing to cancel, squares and square roots cancel, exponents and logarithms will cancel each other out if you set them up correctly.